Greetings, everyone. I hope this video finds you doing well. We are going to continue our journey with the digital down converter, and we are going to implement this digital down converter in Simulink. So we're going to make a Simulink model of the digital down converter. And if you are unaware or don't know what a digital down converter is, I encourage you to watch my previous videos, and that will help you to bring you up to speed. Um, so we start with our incoming science signal, which in our case will be a chirp signal. We're going to use a chirp, which is a signal whose frequency varies with time, and it is used a lot in radar applications. So we take our signal through our ADC, we have a specified sampling rate, right? And then we are now in the area of our FPGA where we first have a mixer. And if we want to see a select range of frequencies from our incoming frequency, we would then mix our signal with a certain frequency. In order to see that frequency, we would apply a low pass filter because whenever you mix a signal, um, you will get a image of that signal from the sum products that you may not want. So you low pass filter it. And now that you have your frequency of interest at a lower data rate, you then apply a downsampling parameter, M. And that way you can reduce your sampling rate in the discrete domain so that you're not handling the number of samples you were when you applied your FS, your original FS to your ADC. So under the hood of this is our design, and we're going to walk through the design. Um, all right, I guess we should start with the chirp signal. So we are determining what our chirp parameters will be, and I modeled this based on an atmospheric differential dual band radar program that I have in my lab, where my initial frequency is 10 megahertz, my target frequency is 20 megahertz, and I have a target time that is based on my sampling frequency here. And so these are the parameters for your frequency sweep, for your chirp. And I have a certain sweep time. And for certain applications, your target time and your sweep time may differ, but in my case, I made them equivalent. And it's important for you. Oh, okay, this is interesting. All right. So our sample time is really 1 over FS. That's really what it should be. Um, but it worked. So that's interesting. So these are the parameters that you need to set for your chirp signal. Again, this is an experiential learning. And what motivates students when doing experiential learning is that the professor doesn't tell you every detail of everything, that certain things that you feel you're in doubt about, that you independently go and look at. So in other words, like you want to look at your help menu. You might want to look at radar applications to investigate how a chirp signal works. Okay, so then we press OK. And now we go inside of under the hood of our design. And again, Simulink models are really good to create when you're trying to put together a fixed point model of a implementation you want to deploy on an FPGA, and you want to just check to see if you have your timing parameters would work, or you have enough resources. But usually the hardware description language code that gets generated from Simulink models, this is not traditionally used for spaceflight applications, but it is a path to spaceflight um, missions because it provides a designer with a very straightforward way of demoing a technique that you will be utilizing on an FPGA while preserving the time. And so once you have determined that a design would meet the requirements and timing and resources for an FPGA, then you can carefully go and code the design on space qualified hardware description language. And for that, you would need to understand how hardware description language works. Okay, so this is the process of getting to the FPGA. Um, and so, first of all, we use hardware description language blocks, HDL blocks. And it's important to note that everything under this hood can be eventually deployed on an FPGA, with the exception, oh yeah, everything in this um, design. The chirp cannot. You will need to generate it in a different way. So, in order to mix our frequency with our, to create the mixing parameter, we are using an NCO. So we're using a hardware description language um, numerically controlled oscillator with various parameters that would help us to look at our frequency of choice that we are looking for in our incoming sinusoid chirp signal. Okay? So these parameters we are going to set in our MATLAB script that I'm going to show you in a moment. But this is our mixer, this NCO. And so we take our incoming signal, we put it through a mixer, and then our low pass filter is made from our traditional convolution structure block that many of my students have already built when they start my class within the first 2 weeks. So when I teach convolution, I teach the equation in terms of the implementation and mathematically in a Simulink kind of model. So they're able to see the mathematics implemented on hardware. All right. So we have our incoming signal. We have the chain delays and gain blocks here. And if we open this up, we have H of 1. Okay, so that is our one of our filter coefficients, that our eventual filter coefficients, H of 2, H of 3, going up to H of 16. So I start from 1 to 16. So if you have done a traditional uh, uh, filter implementation such as this, you probably don't have this many filter tabs, so you'll have to expand your structure. And so you should know how to do that. Okay. And then let's see here. All right, let's go out here. Now we're out here. Interesting. I put my downsampler block outside. Okay, that's interesting. All right. So my downsample parameter is out here. And what I'm showing you is I'm showing you at each stage, I'm going to be showing you our incoming chirp signal. Then I'm going to show you the product after we mix our chirp signal with the 15 megahertz tone that is generated from our numerically controlled oscillator. And then I am going to filter the sum products out of this at this mixing stage. And if you don't know what the sum and difference products are, what I'm talking about, you need to watch a previous video. And then I'm going to show you the results after downsampling. Okay? So everything I'm doing here, I already did in a MATLAB script because remember, that's the first stage of everything. We use our MATLAB script to do what's called a frequency plan. And I showed this in a previous video. Okay, so we're using the NCO as a mixer. We are identifying the parameters of this NCO. And so for this, we use the script that MATLAB gives us. So MATLAB Simulink gives us a sample script, and all I've done is copy and pasted that script. I didn't create this. I just use what MATLAB offers because MATLAB has a really great library of resources that I take advantage of. So you go to help and you can pretty much find everything that you need. What's most important is to read what is an NCO, how does it work, what are the components of an NCO, what's under the hood. And more ambitious students, you should work to generate. Okay, and then it has examples here. And so as you could see, I took all of this information and put it in my script. Okay, so you do not need to reinvent the wheel. You need to use the resources. So I just copied this here, and then and I added a few things. I have my sampling frequency, I have my cutoff frequency that well, it's called my cutoff frequency, but it is the frequency of my, it is the frequency that I wish my NCO to be, and that's 15 megahertz. And then from here, I adjusted my code so that everything is parameterized, and there's two parameters I can change at any time to have a different response. So now we go here down to the low pass filter design. And here I am designing my low pass filter with a specific cutoff because I'm understanding my frequency plan. And I know that after I after I mix my signal with 15 megahertz, I want to make sure I should know where that signal is going to be once I mix it at 15 megahertz. And I want to make sure that I reject the products that come after the signal that I wish to have at baseband. All right. So now here is how I designed my filter. And I'm looking at, okay, what is my cutoff frequency? Well, my cutoff frequency is going to be normalized based on my Nyquist frequency, which is half of my sampling rate. So I have my cutoff frequency, that's 15 megahertz, and divided by my cutoff frequency, my Nyquist frequency, which is Fs over 2. Remember, Fs is 30 megahertz, right? And I mean, 60 megahertz, Fs over 2 is 30 megahertz. So Fc over 30 megahertz, 15 divided by 30, Wn is 0.5. And so we are looking at this translates what FC is in terms of radians per sample, in terms of megahertz. Okay, So now we determine, based on our understanding of utilizing an FIR filter, um, how to determine the filter coefficients for our impulse response. And so we are using a certain window. And remember, we use these windows so that we could design stop band and transition band um, parameters that relate to our what we want in terms of our requirements. So here we're using a Blackman window, and these are the parameters for our low pass filter. FIR1 symbolizes a type 1 linear phase low pass filter. And included in your experiential learning exercise, you will learn about filter design. You will need to watch a video on that as well. And this is how you use the FIR1 function. This is a function in MATLAB. And again, MATLAB has a rich array of help topics, and you can go here and learn about using FIR1. There's also other types of filters you can use as well. Okay, so now we can go and say, well, what kind of filter response am I getting here? And we can look at the filter responses based on running this code. Let's look and see. These parameters here will go into our NCO to generate our 15 megahertz tone. This is our impulse response that we created based on our FIR function here. These are all of the 16 coefficients that we will implement and use in our convolution structure in Simulink. And then this is the frequency response that we will get in our based on our design parameters, which is 15 megahertz, and our sampling frequency, which is 60 megahertz, based on this equation here. Okay. And so the way that we can see how this filter looks in a frequency domain, we use this function called freq z of h. Okay. So we're looking at the frequency response of h and using different windows. And this is an exploration project. You can see if you can get a sharper cutoff, sharper transition band, lower, more of a flat band. You got pretty flat band response right here. Less ripples in the stop band. You can look, there's different windows for those types of exploration projects. Okay. So now we have generated everything here in our, sorry, in our design, and it's going to feed into our model. Okay. And then we run our model. We go back here, and I have all the screens here. So now we run our model. Okay, and see, right here, we see our incoming chirp. I pretty much named my spectrum analyzers so that I can know what I'm looking at. I've sometimes had 20 screens up and I'm like, I don't know what I'm looking at. And so this is our chirp. And this to me is a wonderful way to really explore the digital down converter because you're seeing a bandwidth of data and it's from 10 megahertz to 20 megahertz. And on the left side is our image, right? Okay, so now we see our incoming signal coming in, and now we're looking at the mixing stage, and our entire signal has been shifted down to baseband. This is what we mean by baseband. We've taken the whole bandwidth here and we've taken it to baseband, straddling over zero. So because we mix it with the 15 megahertz tone, that means that we have 15 minus 10 or 10 minus 15. So we're over in minus 5. And then we have 20 minus 15, so we're at 5 here. So this shifted the entire 10 to 20 megahertz tone down to minus 5 to 5 megahertz tone. Have the same bandwidth, same information, everything is shifted to baseband. At the same time, whenever you mix, you have your difference here and you have your sum products over here. And this is what we don't want to carry along with us. Okay, so that's the purpose of our low pass filter. So now we have our low pass filter and we apply our low pass filter and we can see that everything out here is gone or depressed. And we're like, okay, this is nice. And as you can look at your axes, you're going from minus 30 to 30. And so that's still a 60 megahertz. That's based on 60 megahertz, right? Of our sampling frequency is minus 30 to 30. Now let's look at when we downsample. When we downsample, which is downsample by 2, our axes change from minus 15 to 15 because we are now, when we downsample by 2, we have changed our sampling rate from FS equals 60 megahertz to FS over 2, which is 30 megahertz. So now our axes span from minus 30 to 30 megahertz. All right. And so then we still get our minus 5 to 5 megahertz bandwidth. And this is the result of after downsampling. So at this point, I would like for you to go and do the exploration project, replicate what I've done, come to class with more questions, leave your questions in the comments so that I can answer them. And I look forward to hearing from you. Subscribe, like, and have a great rest of your day.